This, you know, comparison.
You want this in our notebook, right?
For the visual Mintac and the Spartan?
Yeah.
No, I want a little sheet, piece of paper, showing the comparison. Right. In other words, I just don't want the numbers. You have to say something about the numbers for those labs. And so those, you know, you could. Look at the data and then determine what you can say about it. I don't know, have you looked at the data? Have you guys looked at the data? The calculations for visual Mintac?
That one's kind of weird.
Kind of weird? Well, then you should say something, this is kind of weird, or the results are kind of weird. And then maybe why? Why is it weird to you?
The numbers aren't even close, they're like the same.
I mean, it isn't even a little bit close, or
No?
every single number?
Yeah. Except for the first question. The other ones were like bad.
Then maybe you should comment on that, you know. So. Okay. And so, yeah, the same, you know, just leaving it blank versus saying, oh, this agreement looks very poor, you know. If you say this agreement looks very poor, that's much better. But if you say this agreement looks very poor and then maybe describe some of it, that's even better, and you get more points, and then continue along those lines. Okay. Does that answer? All right. Anything else? No. All right. So we're officially, I think we're done with chapter 20. So we're going to move on to chapter 24. We just have half of that to cover. But before we do that, there's some stuff from the other chapters between 20 and 24 that I wanted to talk about briefly. Chapters 21 through 23 deal with descriptive chemistry, and those are often skipped, you know, but there's a lot of interesting stuff in them. And so this is chemistry of the main groups, chapter 21, the alkali metals, alkaline earth metals, boron and carbon. Colors. And so just to go briefly into some of this. You know, alkali metals are very reactive. Right? They aren't stable. And so how are alkali metals, how are alkali metals made? What do you think? Well, a metal like sodium. You know, you buy sodium in these bars like this. This is sodium. It's just corroded on the outside there. It's easy to cut. You buy it in bars like this, 500 grams. So half a kilogram of sodium metal. But how is that made? Well, here's one way the sodium is made. And that's this. What is this? This is an electrolytic cell. Anode, cathode. Apply some power, voltage to the down cell. This is molten sodium chloride. What's going to happen? We're going to form molten sodium and chlorine gas here. So it's an electrolytic cell. Same thing with magnesium. You know, all the sodium found on Earth is as the ion. In order to make sodium metal,
How much current do they put through that to separate?
The current will vary depending on the scale of the apparatus. The current's going to just tell us the volume. This has got to have a tremendous amount of current to generate, a significant quantity of chemical. Typically, if you're looking at currents like milliamp or microamp current, you're just forming just a deposit, just a thin deposit. And so if we're looking at currents of amps, currents are very dangerous because the current, they say the voltage doesn't kill you, the current does. And so I'm not sure of the numbers, but it's got to be high.
So like I couldn't do this with a car battery?
No, you could. You could generate a good sized current with a car battery, if you discharge it rapidly enough. I'm not sure what kind of voltage you need for this. Why, are you thinking about trying to make it?
Well, I'm just curious.
Yeah.
It's like easily and do it at home kind of experiment.
Yeah, you could do electrolysis of water using a 9-volt battery. You just aren't going to generate that much. But a car battery, you should be able to generate pretty significant quantities. I mean, you got a lot of voltage there too, so it should work. But you got to make sure you keep the chlorine and the sodium separate, otherwise you're going to have an explosion. Titanium, let's say magnesium. There's lots of reactions here for these. Since we're talking about electrochem, I want to jump to magnesium and then look at this cell. Mark this which page that was. Lithium, sodium, potassium. Oh, this is kind of weird. There's some strange things that happen with bonding when you get into MO theory. This is one of them. When we look at these bonds, this is really weird. Chlorine is a bridging. Do you see this? Looks like each chlorine is bonded. That seems to be against. Normally when we think about chlorine, bromine, iodine in ionic compounds like beryllium chloride, we don't typically think of this as forming. But this is just strange bonding. And you see that kind of stuff in MO, like hydrogen. Sometimes, like in some boron complexes, which are a little earlier. I don't want to flip back and look for it. But you'd have a hydrogen here, hydrogen forming 2 bonds. It's very unusual. And so sometimes you see this, and this is best described using MO theory. Here's another cell. It takes molten magnesium chloride, make magnesium metal here at the cathode, and at the anode, which is graphite here. The cathode is just steel. Steel is much more resistant to attack than magnesium. But the cathode, graphite, forms chlorine. The graphite cathode is encased here in a housing which forces the chlorine out there rather than mixing with magnesium. Magnesium is lower density than magnesium chloride. Magnesium liquid is non-polar. Magnesium chloride is highly polar, and we see that in another electrolysis. That's with 2 molten salts. Some salts are just incredibly hard to melt, and that would be something like aluminum. So let's jump to aluminum. Aluminum's in the boron family. Take a look at this. It's happening here. You know what that atom is? H atom. This is the H atom here. These 2 bonds are indistinguishable. This doesn't make sense. How can you have two bonds to a single hydrogen atom? It's weird. And so you see structures like this. And structures like this are best predicted by MO theory rather than valence bond. And so here's a electrostatic potential map of that molecule. Interesting. structure to it. Boron likes to form cages. In fact, one of the professors at UCLA, I think he was called Mr. Boron or something like that. And his car had something like Mr. Boron, it's the license plate number. He's one of the pioneers. Hawthorne, Professor Hawthorne, one of the pioneers of these boron cages. Because of the bonding on these, what he was into is he was trying to encapsulate these with really lethal isotopes in here. And what he would do is he'd attach like groups here that would be attracted to cancerous cells. And then the bonds are weak enough that he could shine like visible light, and then the visible light would open the cage and release the lethal isotope, literally killing the tumor cell. So that was what he was into. There's a very famous story in UCLA. One of the students there, some of these compounds are very expensive for very small quantities. So one of the students bought I think it was like 100 milligrams of this compound for, I think it was like $15,000. Incredibly expensive. Maybe it was more than that. I forgot the exact amount. Ended up losing it in the synthesis. It's so easy to do. Think about that, because you had way more than 100 milligrams stuff, your separations, and when you're doing these long extended synthesis, it's like doing qual. Each step is critical that you isolate as much of the product as you can. Pure. Before you move on to the next step, this is multi-step synthesis. I forgot how many steps they were doing, but it was a very famous story. So thermite, I think I showed the thermite reaction in the video, right?
Yeah.
Let's look at the production. Here's purification. Lots of different ways to purify stuff. Here's the production. Aluminum oxide is incredibly difficult to melt. And so melting it just isn't practical. With sodium chloride has melting points in the 700 degrees C range. And so that's not so difficult to melt. Same thing with magnesium. Magnesium salts aren't so difficult. Aluminum, very tough. And so they don't melt it, they just dissolve it. And so like dissolves like, right? And so you got to find something highly polar. Aluminum oxide is highly polar, so you got to find something highly polar. Water is not polar enough. And so they use cryolite, liquid cryolite, which is another salt. They can melt easily. Cryolite melts at a much lower temperature, and then they take the bauxite, the aluminum oxide, and dissolve it. So this is just dissolution, solubility. There's some electrodes stuck in here, and the liquid aluminum. Aluminum is more dense, it sinks to the bottom, drain it off. Aluminum. And so these chapters are filled with lots of descriptive chemistry. It's interesting. One time they had water in here. I don't know where they moved it, but they moved it somewhere where I can't find it anymore. I think they just got rid of it. But they talk about deionized water versus distilled water versus soft water versus hard water. They have two types of hard water, permanent and temporary. You heard of that? Well, what kind of water do we use? Do we use distilled water? We don't use distilled water. You know why? We don't use distilled water because it's too expensive. distilled water, because to get distilled water, you have to heat it up and boil it and then condense it. Instead, we use deionized water, which is much cheaper. And so what's the difference between deionized water, DI water, and distilled water? DW water. Distilled is DW versus deionized, DI. Well, the difference is how it's purified. You know what water softeners? You know, what does a water softener do? Does a water softener purify water? No, what water softeners do is they take like permanently hard water. Permanently hard water has like 2+ cations and 2- anions like carbonate and sulfate and 3- ions like phosphate. And so it's got those high charged ions which lead to precipitate. And so what soft water does is it exchanges all those cations for sodium ions and all those anions for chloride ions. And so what you're doing is you're taking the hard ions, you know, the high charge, big charge density ions, and replacing them with soft ions like sodium ions and chloride ions, which are less prone to precipitate. And so that's it. And so soft water is not pure. Soft water is just, we got salt in it for sure, sodium chloride. Well, to prevent sodium chloride from messing anything up, we have deionized water. Deionized water uses ion exchange. Ion exchange is the same thing that they do with soft water, except the ions are different. For DI water, you know, we have these tanks like this upstairs, and what they do is they fill these tanks up with resin. This resin beads here. And these resin beads, they'll take cations and replace it with H+, and anions and replace it with OH-. The H+ and OH- is no problem because those will react to form water. And so for deionized water, it should get rid of all the ions. But what about, you know, the things that aren't ions? What do we do about those? So that's, you know, one of the good things about distilled water. You know, distilled water leaves, you know, or gets rid of all the impurities, including molecular as well as ionic. Whereas deionized just gets rid of these. And so we could have like an activated carbon. You know what activated carbon is? Activated carbon is a carbon that has a very porous structure. And they're like molecular-sized pores in activated carbon, and so the molecules get stuck in the pores of activated carbon. And so that can help get rid of the molecular contaminants. This would be DI.
That's what they use for the carbon filters, like for Brita filters, right?
So yeah, activated carbon, right. Well, the best water, you know, DI is typically thought of as higher quality, higher purity water than DI, distilled water, higher quality. But the best quality water is a combination of techniques. You know, if you want ultra high purity water, you first take deionized water, and the deionized water, then you distill it. You do a DD. You know what DD stands for? DD stands for double distillation. It's a very common technique. So you distill it once and then distill it twice. You do double distillation and then you hit it with UV. And so after doing DI and DD, then the water is pretty pure. It's very high purity water. The cost per gallon of that water is very expensive. So, apparatus. Okay. So a little bit about the water here was in this chapter. And then we're going to move on to some stuff about metals. You know something about the iron, cobalt, and nickel? Well, all metals, let's back up. Let's look at metals. We'll look at some of the properties of metals. Some of the properties that are going to be interested, that we're going to be interested in, are the electrical, magnetic and optical properties of metals. Okay, metals conduct electricity, right? And so this is something that I didn't cover in Chem 1A. If you go back to chapter 11, when we think about the electrical properties, we think about band theory. Why are metals good conductors of electricity, or what is the theory underlying that? And so band theory is just simply, it's MO theory applied to metals. Or not just metals though. MO theory, I should be more general. It's MO theory applied to solids. So this is back in chapter 11. So what is MO theory? MO theory is molecular orbital theory. In molecular orbital theory, we take two atomic orbitals. So let's say I have a lithium 2s orbital here, and another lithium 2s orbital here. And so what do I do with these two 2s orbitals? I do an LCAO. An LCAO stands for linear combination of atomic orbitals. LCAO is your basic fundamental concept of MO theory, right? Two atomic orbitals will form two molecular orbitals, like this. This molecular orbital we call a, what type? Sigma 2s. This one would be a sigma star 2s. This would be for an Li2 molecule. And so then we fill it. This would have two electrons in here, this would be empty. And so these are our MOs that result from this. What band theory does is it doesn't look at small molecules, it looks at solids. Solids will have a lot of atoms. For example, solid lithium is going to have a lot. And so what happens as we add more atoms to this? Well, if I add 3 atoms now, 2 lithiums on this side, 1 lithium on this side, what am I going to do? I'm going to do an LCAO. LCAO only allows for the combination of 2 atomic orbitals, like this, to form 2 molecular orbitals. But what about the third atomic orbital? And so I have my bonding orbital here, and then this one's called a anti-bonding. And the third molecular orbital has nothing to LCAO with, right? And so this third one's just going to sit in the middle. That third one is going to be called a non-bonding MO. It's just stuck. And so this bonding one is an MO. This anti-bonding is an MO, but this third one's just like an AO, an atomic orbital that's just stuck. It's not bonding with anything. Until I get a 4th lithium. If I get a 4th lithium, then that third one can do an LCAO with the 4th one, and then what's going to happen is I'm going to form 2 here, 2 bonding MOs, and then 2 antibonding MOs. And it turns out that energies aren't exactly the same here because of the way they combine the wave function. And so that's with 4 lithiums. Well, if I have a solid, a solid's going to have an Avogadro's number typically. And so we'll take LIN, it's the Avogadro's number's worth on this side. And the Avogadro's number's worth of lithium on this side. And then we do an LCAO for those, and we end up with an Avogadro's number's worth of what we call bonding MOs. And they aren't all the same energy, but they're going to be tightly spaced like this. You know, so many of these extend to about here. And so we call this a band of MOs. It is quantized because, you know, each MO has a little energy gap from the other. But it looks continuous because they're so tightly packed, you can't really see the gap. And so essentially it is a continuum of MOs here for the bonding. Then the anti-bonding MOs would be up here. These would be empty. And so we just have a band of anti-bonding MOs here. Here's another band. And so this is fill, you know. We call this one, we have a name. This is the bonding one. This is called the valence band of MOs, or just valence band. This empty one up here, this is called the conduction band. It's called the valence band. Why? Because, you know, that's the highest energy, right? The highest energy electrons here, basically. So if we have an electron here at the top of this valence band, then what's the gap to the next orbital? Well, let's say it's at the very top. Well, the gap, there's no gap here, so the next orbital is right here. And so if this electron just pops up into the conduction band, it pops up into an empty orbital. Now, molecular orbitals are delocalized over the entire structure. And so if an electron pops up here, that electron has the whole orbital to move in. And so this is the origin of the name. The conduction band is because if an electron gets into the conduction band, it can conduct electricity. Well, lots of electrons can get into the conduction band because the amount of energy required to promote an electron up to the conduction band is just thermal energy. And it's pretty much just right there, and that's it. And so metals have what we call a zero band gap. If we look at something like diamond, we're just taking carbon atoms here, N carbon atoms here, N carbon atoms here. But the bonding interaction is much stronger for diamond. And so when we do the LCAO, the bonding MOs are way down here. So it's going to form a band of bonding MOs, which we call the valence band, because that's where the electron. But it doesn't quite reach up to the antibonding MOs, which is called the conduction band here. And what results is, actually, make this a little more even. What we see here is a large band gap. So if we have an electron down here at the top of the valence band, in order to promote it here to the conduction band, it usually requires about UV. Pretty high energy, UV. Whereas over here, it's just thermal energy, just temperature to do it. And so the only way to make diamond conduct electricity is by shining a lot of UV at it. And then, how many of these do you generate? Because electrical conductivity depends on three things. Let's talk about electrical conductivity. Yeah. Electrical conductivity is going to be proportional to N mu E. N is the number of charge carriers. Mu the Greek symbol mu, this stands for mobility. And E is just the charge on the charge carrier, because the charge carrier doesn't have to be electrons. The charge carrier could also be ions as well. Ions will conduct electricity as long as they have mobility. And so here, you know, we aren't going to get, actually, we have a lot of carriers, electrons here, but there's no mobility, because in order to have mobility for these electrons, it has to get promoted into the conduction band. And that doesn't really happen. So. Diamond's what we call an insulator, because it's going to have very, very low electrical conductivity. Whereas lithium, something like that, would be a metal. So this is an insulator. Lithium's a metal because metals have metallic conductivity. That's one of the definitions of metal. They have electrical conductivity above a certain point. There are things that have electrical conductivities between metals and insulators. And it would be something like silicon. Silicon kind of has the structure of diamond, but the bonding is not as favorable as diamond. And so silicon, you know, we'll form our bonding MOs and we'll form a band down here. And then our anti-bonding MOs will form another band up here. This should be symmetric. And then the band gap is between 0 and large. Here. In other words, the band gap is typically around visible light. And so visible photon comes in here, hits this electron, and can promote it. Like that. Since it's only visible light, you know, as long as there's visible light shining on silicon, it's going to conduct electricity. Well, it's not a very good conductor. It's a pretty poor conductor because we don't promote that many electrons up here for silicon. Okay, so that would be the electrical properties.
What about graphite versus diamond?
Graphite versus diamond. Well, diamond's an insulator. Graphite is a good conductor of electricity.
So then is the gap?
The gap is here. Take a look at the gap. Graphite. This is graphite here. You know, as we add more and more atoms, and so here we got three atoms. We got anti-bonding, bonding, and non-bonding. So 4 and go on. And so when we get a lot of these, what happens is something like this. We'll get a conduction band, and they up here, and the valence band here. This would be similar to graphite. Now, graphite, you know, you could explain the electrical conductivity other ways too, because graphite has a delocalized pi bonding network, and so you can think of electrons being mobile over the delocalized pi bonding network because all the p orbitals are lined up. And so that seems to make sense because graphite is what we call an anisotropic conductor of electricity versus an isotropic conductor of electricity. anisotropic just means that its electrical conductivity depends on orientation. Whereas isotropic means that property would be independent of orientation. And so when we look at graphite, we got the delocalized pi bonding network here. And so graphite is a great 2D electrical conductor. It can conduct electricity in the x direction, in the y direction, but in the z direction, it's an insulator. It cannot conduct electricity in the z. And that's because of the way the pi's are oriented. In the z, you'd have to jump from one graphite to the next graphite sheet. So there are different ways we could look at something like that, graphite. And so it's going to have a more complex. All right, let's electrical conductivity. So one of the things that we try to understand is predict something like temperature. You know, for metals, what would happen with temperature? If I increase the temperature of a metal, does its electrical conductivity go up, go down? What happens?
Top down.
Yeah. What happens is, as the metal gets hotter, mobility is inhibited. Why is mobility inhibited in a metal as it gets hotter? It has to do with the vibrations of the atoms. You know, as the atoms are vibrating more, you know, we can think of the electron traveling through a metal crystal. It's going to be impeded in going from one end of the crystal to the other. And so it's a mobility. What you can do with the metal is cool it down. You know, the colder the metal is, the better it conducts. And if you continue to cool it down, eventually you'll hit something called Tc, which is the critical temperature, which is different than the critical temperature that you saw in the phase diagrams. This critical temperature is the temperature at which it will start to superconduct. That is, the vibrations have been so minimized that the electron just has a straight shot across there. And it'll begin to superconduct. So most metals will superconduct at low temperatures because the mobilities can be enhanced due to lattice vibrations being minimized. How about a semiconductor? What happens with increasing or decreasing temperature to a semiconductor? Would its conductivity increase or decrease? What do you think? On the one hand, well, increasing temperature depends on how big this gap is, right? But on the one hand, you might think it's like a metal. You know, the more temperature, the higher the temperature, the more vibrations, the more the movement of the electron is impeded by those vibrations. But it turns out in semiconductors and insulators, the higher the temperature, typically the higher the conductivity. And the reason for that is because of the defects that get introduced at higher temperatures in these. Well, what we could do is we could introduce defects on purpose rather than heating it up to high temperature and having defects occur random. And the way we can introduce defects on purpose is by doping semiconductors. Doping semiconductors, you're just on purpose, you're adding small amounts of impurities to create these defects that will increase or enhance conductivity. So adding small amounts to increase conductivity. And so here, we call this intrinsic because this is just pure. This is normal conductivity. But we have doped silicon. Doped silicon we call extrinsic because we're not just relying on its intrinsic electrical conductivity, we're introducing the other atoms to create defects. And so there are two types of extrinsic semiconductors. There's something called the N-type. An example of N-type would be like phosphorus doped silicon. Silicon in these structures likes to form these sp3 tetrahedral units. Right? But phosphorus, silicon likes to form 4 bonds, like carbon, but phosphorus likes to form how many bonds? 3 or 5. 3 or 5 bonds. Well, if it's stuck in this lattice, the phosphorus is going to try to form 4 bonds. This is a tetrahedral lattice, right? And so the phosphorus is just stuck as an impurity in the site where silicon should be, and that should be tetrahedral. Now, phosphorus has how many valence electrons? It has 5 valence electrons, so it should form 5. Well, it's going to use 4 of its valence electrons here, but the 5th one is just stuck, not bonded to anything. So this would be something like a radical, free radical, or a dangling bond. It wants to bond to something, but it can't right here. And so what that's going to do is it's going to introduce defects into the band structure here. And so if I look, here's my valence band, we'll abbreviate VB. Here's my conduction band, which is empty, CV. Now, this is going to be localized on an atomic orbital on phosphorus. And so it's non-bonding. Non-bonding is stuck in the middle here. Well, it turns out these non-bonding are stuck right below the conduction band. So if I have one phosphorus here, there's 1 electron, another phosphorus, another electron, so on, depending on how many phosphoruses I incorporate in here. Now, the gap between this state and this is thermal energy, and so it requires pretty much no energy to promote. And so take that electron, take this electron, promote it here, take this electron, promote it here. And so the more phosphorus I put in there, the higher the electrical conductivity I'm going to get over and above intrinsic. It still has intrinsic conductivity. Visible light hits here and bounces it up here, but this is going to be much higher. Electrical conductivity. And then there's another type of doping called P-type. P-type would be boron-doped silicon. How many valence electrons does boron have? 3. Boron has 3. We'll form a bond here, form a bond here. What's going to happen with this other silicon? This silicon will have dangling. But this boron doesn't form. It's going to have an empty orbital here because the boron, boron's typically what? sp2 hybridized? But in this case, this boron's going to be sp3 hybridized. And it's going to have 1 empty sp3 orbital. And so if I look at the valence band here, right above the valence band are going to be these empty sp3 orbitals on boron. Well, what can happen is an electron can jump into that sp3 from the valence band. This is thermal energy. So electron jumps here and creates what we call a hole. Holes left behind. So each electron that gets promoted leaves an imbalance of positive and negative charge. Now, are these electrons capable of reaching the conduction band? Only with visible light, then it's not that much. But what happens is this. Here, in order to conduct electricity, we don't have to have mobile electrons. We just have to have mobile holes. But if you think about holes, I mean, what is a hole? Is a hole an anti-electron? You know, is that what a hole is? Here? No, a hole is just having more protons than electrons. That's what results in positive charge, more protons than electrons. And so how does a hole conduct electricity? Well, one way is that maybe an electron jumps from hole to hole, right? And the electron jumps here, 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 here. So we have a pathway to conduct electricity. But whatever it is, you know, an electron conducting here by jumping to holes, or an electron conducting here by being in the open conduction band, you know, you think is the same. The charge carries the electron. But oddly enough, even though the charge carries the electron, these both show a measurable difference in their electrical conductivity. That is, you can tell if it's going to be conducting by electrons in the conduction band versus holes in the valence band. And that can be experimentally determined by something called the Hall effect, which looks at the magnetic properties as it conducts electricity. But we don't have to worry about that. All right, that's some electrical properties. What about optical properties? Well, we've been talking about the optical properties already. And so something like diamond, does diamond absorb visible light? Like silicon?
No.
No. Diamond does not absorb visible light. So something that does not absorb visible light is what color? Something that does not absorb visible light has what color? White or colorless. Right? No visible light's being absorbed. Why is no visible light being absorbed in diamond? The gap is too big, right? It's a UV. You know what color silicon is? Silicon's black, which tells me it absorbs all colors of visible light. And it's going to look continuum. It's going to be pretty much a continuum, because here, let's say red is enough to promote it right here. Then yellow, you know, orange, whatever. Yellow, red, what is it? Red, orange, yellow, green, blue. You know, it's just promoting slightly higher, and these energy levels are so tightly spaced, we're going to absorb the whole rainbow of colors, right? There's not going to be any missing parts of it. And so it looks black, whereas germanium has another color. Semiconductors are going to have color because the absorption is in the, or the gap is in the visible part of the electromagnetic spectrum. And so I think germanium is yellow or orange, etc. How about metals? You know, small crystals of metal look what color? Like when you started growing the copper crystals on the copper electrode, what color did those look like? They looked black. It looked like a black precipitate, maybe. Did you see that when you dipped the zinc in the copper solution? A black precipitate form? No? Some of you did? Yeah, the black. So metals are either going to look black or they're going to be like a mirror, you know? A mirror, what does a mirror do? It reflects all the colors. And one way of thinking about a mirror is it absorbs and emits all colors of the rainbow. And so a metal it makes sense because a metal has no gap, and therefore it could absorb all energies of thermal and visible light, thermal being infrared. Okay. And so there's some optical properties of some of these things as well. Let's see. back here. This is one model, the electron C model. Here's a band, energy band here. They just show a blend right into the other. The antibonding and the bonding MOs just kind of blend. That scenario would be like B here, where the blue is the valence bond, the white here is the conduction band. So we've got valence band, conduction band, bonding, antibonding, they're just overlapping. Is there a band gap here? No. And so it takes thermal energy just to promote an electron up here. MOs are delocalized over the entire structure. So once up there, it can easily move. This is a little different. This is showing a half-filled band. If we have a half-filled band, it should conduct just as well as metal does because it takes no energy to promote it to an empty MO. Pretty much. This is a semiconductor, with some gap here. And as the gap changes, the color of the semiconductor will change depending on how big the gap is. And the insulator has a very large gap called band gap, like diamond. So here we have an N-type semiconductor and a P-type semiconductor. And if you put together an N-type with a P-type, you can generate something like this, which is a photovoltaic cell. You put the P-type silicon hit by sunlight, N-type silicon here. And so at the anode, we generate the electrons. Cathode, we consume the electrons. So, photovoltaic cell. All right. What about magnetic properties of metals? All right. Can you give me the electron configuration for iron? Iron 2 plus and iron 3 plus. Give me those electron configurations as a review, and then we'll take a look at that. Right back.
Really?
Yeah.
So what did you have for iron? Argon,
4s,
4s,
3d6.
3d6. 4s, how many? 2. Iron 2 plus.
The same, but it's 3D4.
Argon, the same but 3d4.
It's 4s2.
3d4.
No.
No. You know, we lose the 4s electrons before the 3d. And so it's just 3d6. Iron 3 plus, the argon, 3d5. Now, we ask ourselves about the magnetic properties of these. And one thing you'll note, it says iron. Is this diamagnetic or paramagnetic? And so we draw out these orbitals here. We have 1, 2, 3, 4, 5 d orbitals. And we fill them with 6 electrons. 1, 2, 3, 4, 5, 6. And this results in a paramagnetic atom. Paramagnetic atom. We do the same thing. This should be paramagnetic. This should be paramagnetic. And so paramagnetic versus diamagnetic should be easy. Paramagnetic means you have unpaired electrons. Diamagnetic means all the electrons are paired. Well, there's one more, and that is, this is also what we call ferromagnetic. Iron, cobalt, and nickel are ferromagnetic materials, whereas something like any of the others, ruthenium, palladium, platinum, those are just paramagnetic materials. And so what's special about iron, cobalt, and nickel that make them ferromagnetic? And what we do is, just combine all this. This is going to have a paramagnetic moment. And so let's say this is an iron atom. It has 4 unpaired electrons, which is going to result in some kind of magnetic moment with a north pole and south pole. It's oriented like this. And so in a ferromagnetic material, what happens is all these line up. And so we form magnetic domains like this. So if you have a crystal, the net magnetic moment is lined up. Whereas in a typical paramagnetic material, the magnetic domains point in any old direction. They aren't all lined up. And so this would be a paramagnetic. And so this is not really, it is paramagnetic because it has unpaired electrons, but it goes a step beyond that. And so if you have a sample of iron, then we have lots of these crystals. There's another crystal. Here's another crystal. All these crystals are put together, and each of these crystals has a magnetic domain that's all lined up, but not necessarily in the same direction. In an alternate. And so what we could do is we could add these up. If we add all these, we get a net magnetic moment like this. This gives us a net magnetic moment like this. This one could have a net magnetic moment like this, right? And so in a paramagnetic material, the net magnetic moment just extends to the atom. In a ferromagnetic material, it extends to clusters of atoms, crystal like this. And so what you could do with a ferromagnetic material is you could put this into a magnetic field, an external magnetic field. And so let's say we put it into an external magnetic field that's very strong. What happens with a strong external magnetic field is it lines up these magnetic domains like this. So all these individual magnetic domains will point in the same direction. And when that happens, we call this a permanent magnet. There could be other things, you know. For example, if we have molten iron and we just let it cool slowly, molten iron cooled slowly in the presence of a magnetic field will align all the crystals, magnetic domains, in the same direction. And so it'll be magnetized once it solidifies. But if we have something like this where there's little differences in the crystals, then we can magnetize the iron. We magnetize the iron by putting it in a strong magnetic field, which lines it up, but it's not going to stay this way forever. Because eventually it will become demagnetized, and you'll have to remagnetize it, let's say, something like that. Paramagnetic materials, the magnetic domains don't extend from atom to atom like they do here. That's because the atoms are quite big. And so this atom doesn't really care what this atom's doing. You know? And then you have paramagnetic materials where the atoms are small. If the atoms are small, then the domains will try to orient themselves like this so that they're anti-parallel. And so the atoms are too big here. The atoms are too small here because the interaction is too strong. The interaction is too strong, they'll try to do this. And then we have some medium-sized atoms which would do this. And so the atoms are just the right size. And so what's special? Well, the atoms are just the right size to orient their magnetic moments. This. Okay, so that's some magnetic properties of the metals. Now, what we're going to do is we're going to focus on these, ions. When we focus on the ions, we have to worry about, complexes and what species are bonded to those ions. And so we're going to move on to transition metal complexes. And look at the optical and magnetic properties of transition metal complexes. This is chapter 24. And so I'm going to start kind of at the end of chapter 24 and then work back to the structure. The complexes have very strange colors. Let's take a look at some complexes here. Some colors to these complexes. Okay. All these compounds here have cobalt 3 plus as essential metal. So this is a cobalt 3 complex, cobalt 3 complex, cobalt 3 complex. But their colors are totally different. And so when we think about colors, normally when we think about colors are a result of promotion, shining visible light on something and then promoting what? An electron from a lower energy to a higher energy level. And so we call those electronic transitions. And so the color is usually a result of electronic transitions, but when we look at cobalt 3 plus, how many d electrons does cobalt 3 plus have? Well, let me ask you, how many 4s electrons does cobalt 3 plus have? How many 4s electrons? None. How many d electrons? Well, there's a trick. And so if you start at cobalt, you go +1, +2, +3, it has 6 d electrons. And so electron configuration of cobalt 3 plus is argon 3d6. What about cobalt 2 plus? And you do cobalt +1, +2, is number 7. And so that means D7. And so all of these complexes, have cobalt 3 plus, and all the cobalt 3 plus is the same. Cobalt 3 plus is argon 3D6. And so why are those all giving such dramatically different colors? So we have to look at the theory underlying this. Looking at the theory, we have 2 theories describing the color and magnetic properties of transition metal complexes. One theory is called crystal field theory. The other is called ligand field theory. Ligand field theory is not described here. But crystal field theory is a simplified version of ligand field theory. And so both theories arise from quantum mechanics. This is quantum mechanics being applied. Quantum mechanics being applied to complexes, it's called crystal field or ligand field theory. And the difference is in the rigor. And so what's the difference between valence bond theory and MO theory? Well, both theories are the same because they both originate from quantum mechanics, right? And so in reality, there's only one theory. The one theory is quantum mechanics, but when you apply it to little things like bonding or whatever else, then we'll subcategorize it. And so this is just quantum mechanics applied to the complexes. And so the difference between valence bond theory and MO theory is what? Well, valence bond theory is just a simplified version of MO theory. And so, in other words, valence bond theory makes some assumptions or simplifications that make it easier to deal with, a lot easier. And so, most of the stuff you did was valence bond, than some MO. Well, the same thing. The difference between crystal field theory and ligand field theory is that they're both based on quantum mechanics, but one is simplified with simple assumptions, and that's crystal field theory, versus ligand field theory, which is a more rigorous quantum mechanical treatment of these. And so, crystal field theory would be analogous to valence bond, and ligand field theory would be analogous to MO. Except there's one major problem here in using that comparison. And that major problem is that valence bond theory fails for transition metal complexes. And so you cannot use valence bond theory. So crystal field theory goes a step beyond that. Well, what does crystal field theory do? Well, now let's look at a complex of cobalt 3 plus. And let's look at the bonding in this. And so I've got a cobalt 3 plus like this. And if I'm looking at a hexamine complex, I'm going to have 6 amines attached to this in an octahedral arrangement of ligands. The nitrogens attached here. So that's why these 2 amines are backwards. But anyway, this is the hexamine cobalt 3 ion. Describe the bonding here. Well, it looks like octahedral. And you're probably tempted to say, well, that looks like sp3d2 hybridization, right? Hybrid orbitals. But you shouldn't say that because sp3d2 would be well, hybrid orbitals can be used in both MO and valence bond, but I was thinking, this is sounding like valence bond theory. And so you're tempted to use valence bond theory. Well, valence bond theory, we look at the electrons. So cobalt 3 plus, how many valence electrons does cobalt 3 plus have? Does cobalt 3 plus have 6 valence electrons?
Yes.
2 valence electrons? 3 valence electrons? How many valence electrons does cobalt 3 plus have? 6? Yeah. And those valence electrons, well, it's got to have 6 valence electrons because it makes 6 bonds, right? 1 valence electron per bond. Does it make sense? And therefore, we could get something like this. We got the 6 and then 1 electron from nitrogen, 1 electron from cobalt. We form these covalent bonds. But if you go back to the beginning of the semester, we talk about these bonds. These bonds are coordinate covalent bonds. Coordinate covalent bonds means both bonding electrons came from one atom. Which atom did both bonding electrons come from? The ligand, right? Ligand is an electron pair donor. And so how many electrons did cobalt-3 contribute to the bonds here? None. And so the answer to this is, how many valence electrons does cobalt-3 have? 0. You know what we call these D electrons here? We don't call them valence electrons, we call them core electrons. These are inner shell electrons. Even though it's not filled, these are still core electrons. Which is important in size and shielding and all that stuff from earlier. And so, where are these electrons then? I'm looking for these electrons here. Do you see the electrons here? Do you see the electrons here? No. The electrons aren't here. Where are the electrons? The electrons are in the core, okay, of the cobalt ion. They're located in the core. These D6 electrons are what we call non-bonding core electrons. They don't participate in the bonding here. In fact, in the bonding, you cannot use valence bond theory. Remember, valence bond theory is the sp3, d2, sp3, sigma bond. We have to use the full MO approach to this. Now, the full MO approach, we're going to generate bonding MOs and anti-bonding MOs. The bonding MOs and the anti-bonding MOs are beyond the scope of this class. We aren't even going to look at those. Instead, this whole chapter is just going to focus, at least the whole second half of this chapter is going to focus on the non-bonding d electrons. You could call these AOs too, atomic orbitals, because they're really just the atomic orbitals of cobalt. There's no, to get a molecular orbital, you have to do an LCAO, which stands for, what was the LCAO? Linear combination of atomic orbitals, which we aren't doing. And so this is non-bonding. These electrons are just sitting there, and there's 6 of them. 1, 2, 3, 4, 5, 6. Just sitting there. Well, it's not exactly true that they're doing nothing, because they're actually doing something. You know what they're doing? They aren't bonding. They aren't neutralizing anything. They're interfering with the, you know what they're interfering with? They're interfering with the
With the visible light.
Coordinated covalent bond.
They're interfering with the ligands, or vice versa. The ligands are interfering with the non-bonding electrons. In other words, it would be nice if they just sat there and minded their own business, but they don't, because the ligands come in, and even though these d orbitals are just sitting there, these d orbitals have electrons in them, right? 2 electrons, 1 electron, 1 electron, 1 electron, 1 electron in cobalt 3+. Now the ligands are electron pair donors. In crystal field theory, you just treat these as point charges, just negative charges coming in. In ligand field theory, you look at the MOs that form here. But we're just looking at the negative charge. So we have an octahedral arrangement of ligands coming in here, and each ligand is donating negative charge. if I have 2 electrons in this d orbital here, what's going to happen? We're going to get repulsions, negative repulsion. And so what's happening is, yes, these ligands want to come in here and bond, but there's some repulsion due to all these d electrons sitting in here. And so what we'll do is draw an XYZ coordinate system and then have the ligands come in along the axis, you know, plus x, plus y, plus z, minus z. And so these ligands come straight into the lobes, you know, of the d orbital here, all of them. Here, not all of them do. Like the plus z and the minus z, there's nothing really repelling them, but these along the y and the x will come straight into the lobes. So there's a negative charge density going to negative charge density, which leads to repulsion. Here, if you look, the ligands are coming between the lobes. If they come between the lobes, the repulsions aren't as great. And so this is what we have. Pretty big repulsions, smaller repulsions. Here, it's coming between the lobes, smaller repulsions. And so normally, d orbitals are what we call energetically degenerate. You know, they have the exact same energy. But what happens is, as the ligands come in, these ligands interfere with these 2 orbitals more than they interfere with these 3 orbitals. And so that creates a splitting in the energy of the orbitals. And so what we have here is this. If we have the free metal line, it's like this. Now, as we try to bring in the, well, this is the free metal ion d orbitals. There's too many lines here, but that's it. Here are the d orbitals in a field of negative charge. This would be an isotropic field. Did I talk about isotropic and non-isotropic with the graphite? Isotropic means it's the same in 3 dimensions, but actually forget about it. And so here, the negative charge density is going to repel, but it doesn't repel all these orbitals evenly. It repels 2 of them more significantly because the ligands come straight into the lobes. That would be the dz squared, dx squared minus y squared. And 3 of these it repels less significantly because it comes between the lobes, the xy, and the xz, and the yz. And so we get a splitting. So the 5 orbitals are no longer the same energy. We have 2 high, 3 lower. This is what results in the color of these, because what happens is we get a gap. You see the gap here? And the gap, this is called the crystal field splitting energy. It's given by delta O. O stands for octahedral. This gap is typically in the visible range. If this is in the visible range, what happens is visible light comes here, hits an electron down here, and promotes it to this, giving it color. The gap depends on how strong that electric field, that is that negative charge density coming in, is. And so the strength of the interaction depends on the ligand. And so, for example, here, these ligands tend to generate strong electric fields, that is fairly high negative charge density. And so something like cyanide, nitrite, ethylene, diamine, pyridine, amine, these generate large deltas because these concentrate that negative charge, resulting in larger repulsion. These generate smaller deltas because they aren't as, I guess, interfering or as negative, as highly, as high of a negative charge density on those. And so what we'll see is, this is not to scale, but let me just show you what we'll see over here. This. What we'll see is this. An amine generates a high field which results in larger repulsions. The larger repulsions means a bigger gap here. A fluoroligand generates a weaker field, which means a smaller gap here. And so, strong field, big gap, weak field, small gap. Now, having a big gap versus a small gap is going to affect its magnetic properties and its optical properties. And so let's look at this in terms of magnetic properties. Having a big gap here means that the Aufbau principle holds. We fill the lowest energy orbitals first. Having a smaller gap here means something might override the Aufbau principle. Normally we fill the lowest energy orbitals before moving to the higher energy orbitals. But in this case we don't do that because of something called pairing energy. And so let's talk about pairing energy here. Let's do our fourth electron. This is the normal way we fill our fourth electron. We pair it. Well, pairing electrons in a single orbital results in repulsions. And so sometimes that's not so favorable, but we have no choice because the only way we can get this one into its own orbital is by promoting it to a higher energy orbital, and that's not beneficial either. And so here we fill the lowest energy orbitals first. But in these transition metal complexes, it turns out this gap is not so huge typically. Even though it's visible light, this is not so huge compared to the pairing energy. And so if the gap is not that big, let's say it's in the infrared, then what could happen is rather than pair it, we could promote it. And so we have a difference in magnetic properties that result depending on the field strength of the ligand. And if we have a big delta here, which means we have a strong field ligand, like a nitrogen or a carbon donor is the strongest, then this is going to be less paramagnetic than this. In the presence of weak field ligands, we'll promote rather than pair, resulting in 1, 2, 3, 4 unpaired spins per atom versus 2. So this will generate a much stronger paramagnetic effect than this one here. And so going back to this, we can see this in action depending on the strength of the ligand. Here, strong field, we're going to pair versus promoting. Weak field, we promote versus pair. And so even though both of these have 6d electrons, they feel totally differently, such that the hexamine complex of cobalt is actually diamagnetic. And the hexafluoro complex of cobalt is paramagnetic. And so the magnetic properties are totally different, as well as the optical properties. Because when we think about promoting an electron here, let's say a photon of visible light comes here, hits this, and promotes it here, versus a photon of visible light comes here and promotes it here. This one, the gap is smaller, so we're going to absorb lower energy colors. This one, the gap is bigger, so we're going to absorb higher energy colors. And so higher energy colors would be like blue, green, violet. So this absorbs blue, green, violet. These types of complexes absorb red, orange, yellow. If something absorbs blue, what color does it appear? Or if something absorbs green, what color does it appear? Well, something that absorbs green appears the opposite, red, right? And so these complexes look or appear low energy colors like red, orange, yellow. These complexes here appear high energy colors like blue, green, violet. And so we'll stop here since we're out of time. And then finish this up.